Okay, so now we're going to do an example using this ideal transformer to show you how it works. So we've got an ideal voltage source. It's 2500 peak times the cosine of 400. The internal impedance of this generator is 25 ohms plus 5 millihenries. And it is just connected directly to the primary of an ideal transformer. The secondary just feeds a load. It's a tiny load consisting of a resistor and an inductor. It's 237.5 milliohms and then 125 microhenries. This is a 10-to-1 ideal transformer. So how do we use this ideal transformer in this model? Well, the first thing we need to do is convert these inductances of the generator and of the load into inductive reactance. We just do that by multiplying by j omega. So this becomes j times 400 times 5 e to the minus 3, and that's j 2 ohms. And this becomes j times 400 times 125 e to the minus 6, and that equals j 0.05 ohms. So we've done the transformation over. The other thing we need to do is convert the voltage over into a phasor, 2500 angle 0 degrees. So now we've done all the phasor transformations. We're in the phasor domain. We can go ahead and write our loop voltage equations for the primary and secondary. When we do this, we ignore the value of the inductors, and instead we just look at the voltage drop across the primary and the secondary. So if we're going to write the equation for the primary side, it's 2500 at an angle of 0 degrees is equal to current flow, which is, we'll just call it I1, times 25 ohms plus J2. And then we need to add to that V1 because it's a voltage rise. And then on the secondary side, we've got V2 is equal to I2 times 237.5 e to the minus 3 plus j 0.05. And that's it. Those are the voltage equations if we're using an ideal transformer. So very, very simple equations. How do we solve these? Well, we have one more piece of information, and that is V1 over V2 is equal to N1 over N2 is equal to I2 over I1. So let's use the first half of this first. We find out that V1 over V2 is equal to 10 to 1, which tells me V1 is equal to 10 V2. And similarly, I find that I2 over I1 is equal to 10 to 1, which says that I2 is equal to 10 I1. So I can substitute these equations into either this equation or this equation here, and then solve simultaneous equations. So what I'm going to do next is I'm going to go ahead and put them in to this equation. So I need a V2 here. So what is that? That's a V1 over 10 is equal to, now I need an I2, that's 10 I1 times 0.2375 plus j 0.005. I'm going to go ahead and distribute that 10 out. That's equal to I1 times 23.75 plus j 0.5. It's a little hard to read. J5. Nope, j 0.5. Sorry, J5. Let me redo this. I need to multiply by 100 first, or multiply both sides by 10. So that says V1 is equal to 100 times I1 times 0.2375 plus j 0.05. Now I can distribute that 100. V1 equals I1 times 23.75 plus j 5. and that's an I1. Now what I can do is I can substitute this equation into this equation for V1. So I get 0 degrees is equal to I1 times 0.25 plus J2 plus V1. I substitute V1 into that, and I get 500. Angle 0 degrees is equal to I1 times 0.25 plus J2 plus I1 times 23.75 plus J5. Factor out the I1s on the right-hand side. That becomes 2500 at an angle of 0 degrees is equal to I1 times 0.25 plus J2 plus 23.75 plus J5. That's equal to I1 times 24 plus J7. I1 is therefore equal to 2500 volts at an angle of 0 degrees divided by 24 plus J7. That gives me a value of 100 amps at an angle of negative 16.26 degrees is the current flowing in the primary side. I can plug that back into this equations for V1 right here. So I find the voltage across the primary is just equal to 100 angle negative 16.26 times 23.75 plus J5. And that gives me 2427.06 volts at an angle of negative 4.37 degrees. I know from the turns ratio that I2 is just equal to 10 I1. That's equal to 100 at an angle of negative 16.26. And V2 is equal to V1 over 10. So just divide this number here by 10 and I get 242.71 at an angle of negative 4.37 degrees amps and volts. Okay, so that's the end of transformers. So you can go take the practice quiz, or take the online quiz and look at the homeworks.